Well, good morning. Let's get started. I am very pleased to introduce Jianqiang and Jerome on behalf of Professor Antoniadis and myself, who are co-advisors of his PhD thesis. Jerome is a native of China, and he received his bachelor's and master's degree in electrical engineering from the National University of Singapore. His master's thesis was on self-aligned unipolar MOSFETs. I remember that paper. He presented it at 2008 IEDM, the International Electron Devices Meeting, which is the most important conference in our field. And I was really stunned. This was very impressive work, the very first self-aligned planted MOSFET made on indium gallium arsenide to date, up to that point. For that work, he rightfully received the Best Student Paper Award at IEDM that year. He also was a co-author of a paper that received the IEEE Paul Rupp Award in 2008 by that same group in the US, which was on strain silicon MOSFET technology. So that gives you a sense of the range of Jerome's experience and activity. He's been with us at MIT doing his PhD on indium gallium arsenide MOSFETs for future logic applications, and you will see some of his research results today. His research has resulted in papers at IEDM, again, the most prominent conference in our field in 2012, 13, and 14. And in 2014, just last 2 months ago, he received also the Best Student Paper Award. I haven't gone back through the 60 years of history of IEDM, but I don't recall that a student ever won the Best Student Paper Award twice at IEDM. So this is very singular. One of these days I will go back and try to dig this out, because I think this is a very unique achievement. In fact, Jerome has also been selected recently for the Chinese Government Award for Outstanding Self-Finance Students Abroad. This is also an extremely competitive award given by the Chinese government. He was a research intern at IBM T.J. Watson Research Center in the summers of 2012 and 2013. He also belongs to the most distinguished and exclusive club of former 6720 PAs. Some of you have heard me saying this before. I encourage you to volunteer for being PAs in 6720 and other subjects at MIT. And I want to thank him personally for his support in this course while he was a PA. He's also been a great citizen of MIT and the MTL community. He was a member of the Process Technology Committee, and he also was a reviewer of abstracts for MARC 2000. Jerome, thank you very much for all you have done while you have been here, and we're looking forward to seeing a summary of your fantastic research.
Thank you, Jesus. Good morning, everyone. My name is Jerome Lins. Welcome to my thesis defense. The title of my thesis is InGaAs MOSFETs for Logic Applications. This is the outline for my talk. I will first give you a brief background on the topics I'm talking about here, the motivation and the challenge of 3-5 CMOS. And then I will discuss our particular device architectural design and the fabrication process to make it. And then I will give you 2 examples that we have done on studying the device physics for the device we have made. They are the impact of the channel thickness scaling and the physical origins of the off-state leakage current in the high-performance MOSFET in the InGaAs system, followed by conclusion. Arsenic-containing 3-5 semiconductors are famous for their superior electron transfer property. In a modern deeply scaled transistor, in the perspective of transport, what really matters is the so-called source injection velocity. Professor Del Alamo summarized the source injection velocities for 3-5 channel transistor and strain silicon transistors in this graph. It shows that 3-5 transistor can deliver more than 2 times of the source injection velocity at a reduced voltage. That makes it a very promising candidate for high performance and low power applications. The device used for a 3-5 transistor study here is called indium arsenide HAMD. Indium arsenide or indium gallium arsenide are the examples of very high mobility 3-5 semiconductors. HAMD here stands for high electron mobility transistor. It is a type of a field effect transistor architecture that has very similar operation principle as a MOSFET. Our MIT team has a rich technology heritage on the HAMD research. Our alumni has scaled down the HAMD gate length to 30 nanometer, and it was those devices that were used for study here. But despite of the great success used as a learning platform for device physics, HAMD itself cannot be used as a CMOS logic device directly. The reason is because here. Here I show you how a HAMD device looks like. It has a big mushroom gate sitting on top of a wide bandgap semiconductor barrier. It's a so-called Schottky gate. It leaks a lot of gate leakage current. And the removal of the semiconductor around the gate region is using selective wet etch, leading to a long undercut. The fabrication of the gate stems and the contacts using gold-based material, and they are using leaf-off to make it. And these two components are not self-alike. So it yields a long device footprint, for example, 2 micron here. Just as a comparison, here I show you how a modern VLSI device should look like. This is an Intel 32 nanometer transistor. Within 100 nanometers device footprint, you will find the self-alike slit size, the spacers, and the gates. So if you want, you can put 20 of those devices just at the access region of the HAMD. So when I come to MIT in 2009, in my first meeting with my advisors, the following thesis goal was proposed by Professor Del Alamo. We want to make a 3-5 device look as much like silicon as possible and feel as much like silicon as possible, but with competitive performance. In order to realize this goal, we want to fully leverage our technology advantage on HAMD research. For this, let me bring you back to these 2 figures again and identify the key change we need to make this 3-5 device looks like the one below. First of all, we need to use high-level self-alignment. We cannot afford to have separate masks for the front end. The ohmic metals, access region, and the gate has to be aligned to one single mask. Here, I start to have a change of terminology from the silicon convention to the 3-5 convention. Ohmic metal here is an analogy to the slit size of a silicon transistor. Access regions is equivalent to the spacers, and the gate is the gate. We need to also integrate a high-quality gate insulator to suppress the leakage current through the Schottky gate. We also need to scale this dielectric down so that the device will have electrostatic integrity when it scales to small dimension. And we need to fabricate this device using a CMOS-compatible process because this is target for CMOS applications. And for this, we cannot use wet etch and leaf-off because wet etch will result in a long undercut. And we cannot use gold either because it's not a CMOS-compatible material. So in order to realize those goals, we design a very special device architecture and fabricate it with a contact-first, gate-last process, which I will discuss in the next section. First of all, I will give you a process overview how we make this device. The starting heterostructure is grown by MBE from the commercial vendor on the indium phosphide substrate. We carefully design these heterostructures so that you will work with a degree of freedoms for our process. And there are a few heterostructures we have grown in the past few years. The one that yields the most successful device has a structure looks like this. It has an indium gallium arsenide, indium arsenide quantum well channels. The total thickness is about 10 nanometers. And on top of it, there's a thin indium phosphide, etches markers for etch stop calibration, and M+ cap. When we receive this wafer, we clip it into pieces. And then the first step in MTL is to deposit the ohmic metals, which is tungsten, molybdenum, and silicon oxide hard mask. I will tell you later why we need the 2 layers of ohmic metals here. Then we will perform gate lithography to define the intrinsic region. Using a lithotron beam lithography, we can define this gate line as small as 20 nanometer, which you will see later too. And then we etch the silicon oxide and the ohmic metal stop on the 3-5. And then we remove the resist and change the recipe to an isotropic RIE. This allows us to pull in the ohmic metal with respect to silicon oxide gate etch here, and then this is the formation of the access region. Then we perform 3-5 resets. This is a new invention in my thesis. And I will tell you more detail of this process. Basically, you have 2 steps. One is the coring-based RIE to remove partially the semiconductor, and then a digital etch to finally look for the surface you want to stop. Immediately after the last cycle of digital etch, a fresh semiconductor surface is open, and we load it to an ALD system that possesses the high-K dielectric. After that is the gate electrode evaporations, followed by a patterning. Until now, the front-end device is completed. You can see that we only use 1 mask and define all the critical features in this transistor. And after that is the back-end process, which is the rear opening and metal line routing. They are not shown here. To motivate you to continue listening to my talk, let me first tell you that this process works. And here is an example of the fabricated device. You can see this is a quantum well channel. This is a high-K dielectric. This device has a gate length of 20 nanometers. At the time when it is made, it is the smallest functioning 3-5 MOSFET. And you can see that within 100 nanometers device footprint, you will find the ohmic contact, access regions, and the gates all nested very tightly. And here is the output characteristic of this device. Now I hope you are impressed. And let me tell you some critical process units that are allowing us to arrive at this device. Since this is a contact first process, I will discuss the contact here first. Our alumni has developed a very nice refractory metals contact technology on N+ indium gallium arsenide. And in my first generation of device, I adopted that technology and used one layer of moly as the ohmic contact. As you can see, I can scale down the device gate length to a very small dimension, something like 20 nanometer, as early as 2012. But the problem is, we observe a long lateral undercut on the ohmic region here. We later understand the reasons for this undercut from a TEM. As you can see here, the top layer of the molybdenum was oxidized during the CVD oxide deposition. And this moly oxide was easily attacked by the fluorine-based RIE used to etch the molybdenum in this region. So this results in a long undercut. We explore a few solutions for this problem. The one works the best is using the very thin tungsten barrier between the molybdenum and the silicon oxide. As you can see, this device, after adding this tungsten barrier, results in a relatively strict sidewall in the ohmic contact. This allows us to make the contact-to-contact spacing as small as 50 nanometers. So this is a critical technology allowing us to achieve very small device footprint and also making a tight pitch pattern, for example, the one like this. We use this technology to fabricate tight pitch MOSFET array, which you will see later. Next, I will discuss the recess module. Recess has the same meaning as etching. Pre-3-5 recess here refers to the etching of silicon oxide and the ohmic metals. Here, I would like to particularly discuss one technology we developed here, which allowing us to control this access region in a very precise way. As I mentioned before, the access region is equivalent to the spacers of a silicon MOSFET. As you can see, this is the spacer. Its function is to separate the gate and the source and drain silicides so that there's no leakage. So it has to be big enough to prevent any leakage path, but it also has to be small enough so that it does not consume any valuable device footprint. This device has a space of 15 nanometers. So how do we do in our MOSFET? We adopt a method that first developed by our alumni, Dr. Jones. The way to do it is using a right isotropic RIE. It allows us to selectively etch the ohmic metals, but not the silicon oxide on the 3-5 in an isotropic way. By timing this etching, it will results in air gaps, as you can see here. And then the gate is going to be put on later, self-aligned to the silicon oxide. Then this air gap will be the spacer, or the access region. Here show you two examples of this device we have made. For a longer RIE process, we end up with a longer lateral etching, and this is a long access device. And also try to explore how small we can make this access region. The best one I can make is 15 nanometer, matching the dimension of a modern silicon device. And this very precise lateral control of the access region also motivates us to think if we can put another device identical to this one right next to itself. This leads to the fabrication of tight pitch MOSFET arrays. So as you can see here, I show you two arrays. In this array, this is the gate region, this is the contact region. And we have achieved a contact size of only 40 nanometer. This is the ohmic contact, including the ohmic metals. This is the smallest contact ever been demonstrated in 3-5 MOSFET. And by another combinations of gate length and contact length, we can achieve a gate pitch size of 150 nanometer. Again, this is the smallest gate pitch ever demonstrated in 3-5 MOSFET. And let me tell you that this process is easily integrated onto a standard 3-5 MOSFET fabrication and is fully operational. So by carefully measuring and modeling such a device, you can actually study the nanoscale contact behaviors of such a technology. More details is discussed in this paper. Now I would like to move on to the 3-5 recess unit. As I mentioned, this is a new invention in this work. Let me first tell you why we want to invent something new instead of using something conventional. So conventionally, the 3-5 recess in HEMS fabrication is using selective wet etch. As you can see, 2 devices here. It results in a long undercut. For example, it's above 100 nanometers for these 2 devices. In my first generation of device fabrication, I tried very hard to see what is the minimum we can get by controlling the wet etch time and the solution. Here I show the best I can get is 30 nanometer. But even though, when I present this device outside, it was still criticized for being an underlap device. An underlap device will consume a valuable device footprint, and more importantly, this region is ungated, the gate is not covering, and it's uncapped, the M+ is not reaching here. So it results in a large increase of access resistance. So to solve this problem, we think very hard and see what is the alternative. And eventually we develop an alternative in this way. We first use a chlorine-based RIE to etch partially of the cap. It results in self-aligned features to the silicon oxide mask here. By carefully tuning this RIE, we can end up with a very smooth surface. And then the etch depth is not very critical because later we are going to use a digital etch to gradually find the final terminating surface you want to stop. The digital etch technique used here comprises of 2 steps. The first one is low oxygen plasma to oxidize the 3-5 surface and form a native oxide. Basically, this is the etcher. And then the second step is to use diluted sulfuric acid to remove this native oxide. Both of these 2 processes are self-limiting, resulting in about 1 nanometer's removal of the material for each cycle. And the ending surface of these 2 processes is relatively flat, qualified for most applications. One very critical problem in this process comparing to a wet etch is that it doesn't have a selectivity. Both of these processes will etch the semiconductors of those layers in a comparator rate. So this is a problem because if you cannot find the ending surface, it will not be useful. Then we developed techniques to calibrate this etching. This is a fast and accurate calibrations, allowing us to pinpoint the top layers of the indium phosphide. This is basically making use of the wet etch selectivity of the indium phosphide and indium gallium arsenide against certain wet etch recipe. The detail is discussed in this paper. If you can pinpoint the indium phosphide, then you have the freedom to control what is the depth by using a digital etch. As a proof of accuracy, I show you 2 devices here. They are fabricated on the same heterostructure. As you can see, the growth channel is 10 nanometers in the unetched region. By using different combinations of dry etch and digital etch, you can end up with the different thickness in the intrinsic gate regions, 8 nanometer and 4 nanometer, as reprinted. If you zoom in to the 4 nanometers channel intrinsic region, you will see exactly 7 monolayers of atom left behind, proving the accuracy. Now we have the contact, we have the recess. The last ingredient to make a MOSFET is the gate stack. We have gone through several generations of gate stacks engineering. The first generation here, I use a relatively conservative design, a thick aluminum oxide on thick indium phosphide, resulting in a EOT of 3.5 nanometers. EOT stands for equivalent oxide thickness. It's calculated from the physical thickness of these 2 material and its dielectric constant. I'm very excited when I got this device because this is the first decent working device after 2 years of process development. And more excitingly is to see that this device have a very low leakage current, allowing us to scale the EOT down. And then in the next generation, we fabricate a gauge stack like this. We use a higher K material, hafnium oxide, on top of a thin aluminum oxide on the indium phosphide. And the indium phosphide also scaled down, resulting in a EOT of 0.9 nanometers. And here is the device substructural characteristic. Even though the gate length is much smaller than the one above, you can still have a much improvement in the substructural swing. And we also fabricate a device on using this gauge stack on a long channel. And then so we achieve a substructural swing of 69 millivolts per decade. This is the second best value in year 2012 for 3-phase plenary MOSFET. The only one better than this is made by Intel's 66 millivolt per decade. This research is greatly benefited from the multi-university collaborations. Here is one example. In the MSD review, we learned from our colleague from UT Dallas that hafnium oxide itself can also form a very good interface on 3-phi. So this information is quickly feedback to our fabrication. And then in our next generation, we remove the aluminum oxide interfacial layer and directly put hafnium oxide on indium phosphide. The resulting EOT is reduced to 0.6 nanometer. And here shows the same device with the same gate length and overlap with the curve you have seen in the second generation. You will see that in the subterranean region is overlapping on each other. That means there's not much difference on the interfacial quality. But because of scaling of EOT, you can still see an increase of the drive current. Now coming to the next generation, we want to solve another problem, which is for all VLSI device, it's all surface channel device. By the invention of our new 3-phase recess technology, it allows us to stop at any 3-phase surface that we want. So we can remove the indium phosphide by using digital etch, and then we directly put hafnium oxide on the InGaAs channel. Here resulting another EOT reducing. Even though we have using dry etch in the intrinsic regions extensively, you can see that this device still results in relatively good subterranean shrink and high driving characteristics. Also, the gate leak current, even though we use a very thin EOT, is still very good. So this is our latest technologies in gate stack. Just as a recap of the fabrication technology. In the quest for higher device performance, we persistently introduce new features to our fabrications. Over these years, we have performed 4 generations of intrinsic engineering, which bring down the EOT to 0.5 nanometer. And over this year, we use 4 generations of extrinsic engineering and brings down the source resistance to 100 ohm micron. So since this is my 6 years in MIT, on average, each generation is taking about 18 months. So if you are sensitive to this number, probably your next question would be, does your performance scale the same way? Here I show you a representative device performance figure of merit, which is called the transconductant, GM, over the years when I in MIT. You see that it's persistently making progress. We observed 2 very significant increase in the performance. The first one happened here is because of scaling of EOT and the gate length. The second big jump here is happening because the new invention of the 3-phase recess technology, allowing us to bring the M+ so much closer to the gate. And because of those, we represent the world's best performance in 3-phase MOSFET in the last 2 years. If you look at a broader history, Professor Del Alamo summarized the record transconductant for indium gallium arsenide HAMD and MOSFET since their invention. Very interestingly, you will see that the performance of InGaAs MOSFET increased very rapidly in the year 2009. That is at the times where 3-phase CMOS getting a lot of interest and accelerate very fast. The device here is made by Intel. And when I look at this device, it gives me quite a bit of stress. And I'm quite nervous at that time because I was here. And the second big jump happens, I have explained to you here. Another thing worth noticing is the comparison with indium gallium arsenide HAMD. You can see that indium gallium arsenide HAMD has leading this performance since 30 years ago. It was only last year that our device bypasses performance. And I believe this is just the starting. The potential of the InGaAs MOSFET has not been fully unleashed. Probably very soon you are going to see another big jump in the performance of InGaAs MOSFETs. The device technology developed in this work also allow us to explore some unknown device physics that are relevant to the operation of 3-phase MOSFET. I have done several studies in my thesis, and here is a list of them. Because of time, I do not have enough time to discuss every of them in detail. So I'll briefly tell you what I have done for 2 topics here. The first one is the study of impact of the channel thickness scaling to device performance. Let me remind you that we have developed a technology allowing us to precisely control this channel thickness. Let me to be more precise. Let's denote the channel thickness as TC, and TC refers to all the semiconductor thickness after recess, which is above the indium aluminum arsenide here. If you stop at the indium phosphide, that means TC is larger than 10 nanometer and below 30 nanometers. Then it will result in a barrier channel device. If your etchings are TCs below 10 nanometer, resulting in a surface channel device. We find that TC has a very strong impact on the device characteristic. When optimized for the on-state for these particular heterostructures, we find that TC is equal to 9 nanometers. And here I show you the device characteristic of a gate length of 80 nanometers. This is the output, and this is transconducting characteristic. We achieve an R-on of 190 ohm microns, and the GM maximum is 3.1 millisiemens per micron. And it's this very particular device that I discussed in the previous slide, reaching the world records for last year. Here a more systematic graph of the GM and the TC relationship. So here I plot the GM versus TC as at different scale length. You can see that the GM almost always peak at the thickness of TC equal to 9 nanometers. So a reason for this is when the TC is increased above 9 nanometers, the device becomes a barrier channel device, and then you're losing the capacitors. If TC is smaller than 9 nanometers, as the TC scale down, first of all, the series resistance is increasing, and also the transport property of the charge is also degrading, so resulting in a drop of the GM. So it seems the higher, in general, the larger TC is beneficial for the on-state, but it is not the case for the off-state. Here I show you the subthreshold characteristic for two devices. They have the same gate length. You can see that the TC with a thicker thickness is relatively poorer than the TC with a thinner thickness. That is the larger subthreshold swing and the poorer depot. A more systematic graph of the structural effect figure of merit is shown in this graph. I show you the subthreshold swing, depots, and threshold voltage roll-off as a function of gate length for devices with different TC. And this is a very dense graph, but the point to take is if you scale the channel down, you will see a very classic behavior that the structural effect figure of merit degrade very strongly. And you can see that as the TC scale down, these degradations happen at a shorter gate length. But if you examine that even the smaller channel thickness, something like 3 nanometers, we can still see the degradation start to happen at a gate length of about 15 nanometers. So this probably is indications that the plenary transistor device architecture cannot meet the scaling goal for future VLSI device. We probably will need a 3-5 device architecture. So another example I want to give you is the physical study of off-state leakage current in high-performance InGaAs MOSFET. So let me define what is off-state leakage current I'm discussing here first. So the off-state leakage current here is defined at when the transistor is biased at a negative gate overdrive and a high VDS, high drain bias. And you will see that this excess off-state leakage current at this bias condition happens in almost all high-performance InGaAs MOSFET. Two examples. One is the one made by Lund University in this region. Another one is made by myself in this region. The origins of this off-state leakage current is still not known in early 2013. So our high-performance device made in 2013 give us the opportunity to explore this physics. So what we do is just like detectors to unpeel the onion layer by layer. We first isolate the effects from the buffer leakage and the gate leakage. And then the next thing we want to isolate is the Fermi level pinning due to DIT. For this, we performed low temperature measurement. And you will see that the subthreshold swing of those devices is approaching its ideal value when the temperature cools down to 150 K. This N is defined as the experimental subthreshold swing over the ideal subthreshold swing. If it's approach 1, that is ideal. And it indicates that DIT is frozen at low temperatures. And you are going to see the patterns following the classical GATO, which you will see in the textbook. GATO stands for gate-induced drain leakage. Here I explain to you what is a GATO. A classic GATO is happening because you bias the gate at the negative voltage, your drain in the positive voltage. It creates a high E field regions in this gate edge close to the drain. And because of this high E field, it stretches the band and allow a valence electron to tunnel through, and then this electron will collect it in the drain. And then the hole left behind will diffuse to the source. This constitutes the band-to-band tunneling current. So we performed a bias and temperature dependent studies on this off-state leakage current. It really reveals the characteristic of band-to-band tunneling. So this is the first unambiguity evidence to identify that BDBT is really the trickling mechanism. But does the IOF entirely due to BDBT? This is the second problem. This is what people really think in the last years. And we find a counter evidence here. So if this current is entirely due to BDBT, BDBT is happening only in the high E field region. So it's a very localized process. So it should not have a dependency on the gate length. But we find a very strong gate length dependency in our off-state leakage current, as you can see here. So it indicates something else is happening. So what is that? So we find later that this is due to a parasitic bipolar transistors. So the operation is shown here. And as I mentioned before, the hole generated due to BDBT has nowhere to go because this is a floating body channel. They have to go to the source. And then when they go across the source to channel junction, this junction, the barrier have to be lower, which allows a flood in of electrons. This constitutes a large of the electron diffusion current. If you are familiar with BJT, then when you look at this band diagram, it's exactly how a BJT should look like. And equivalently, the source is acting as the emitter, the drain is acting as the collector, and the gate is acting as the base. And this band-to-band generating hole current is the source, it's the emitter at injection, it's the base injection current. Then if it is a BJT, it should be characterized by a gain. Then the gain is, in a BJT, is inversely proportional to the quasi-neutral base width. In this one, it's equivalent to the gate length. And then actually we find this dependency embedded on the off-state leakage current observed in this graph. The detail is discussed in this paper. We can even also pinpoint the base width modulations from this off-state leakage current in our experiment. Then we later developed models to understand this better. Here is the experiment we observed in our device, and here is the TCAT model we built to understand it. And you can see that they end up with a very good match. And there are a few points to take notes here. If you exclude BDBT, then the transistor will just turn off nicely, as shown in the green curve. That indicates BDBT is really the triggering mechanism. Secondly, if you examine the current component in these regions, you will see that the BDBT current is only a very small fraction of it. The majority current is this source electron diffusion current. The gain is about 700. So from this simulation, it also allows us to explore the design concern to reduce this off-state leakage current. And due to time, I don't have the, I will not discuss it here. As extended reading, you can refer to those two papers. So here I come to my conclusion. Starting from HAMD, we want to take the advantage of the HAMD technology advantage we have in MIT. Then we design a very special self-aligned InGaAs MOSFET architecture, and then we fabricate it using a contact-first scalar process. Over these years, we persistently introduced new features to our process module, including the gate, recess, and the gate stack. From those, we achieved some of the device that we can claim is the world's smallest. The smallest gate length, the smallest contact size, the smallest access region, and the smallest gate pitch. And due to this advancing in the fabrication technology, we're also advancing the performance frontier of InGaAs MOSFET. We have achieved certain very impressive figure of merit here. We have achieved a EOT of 0.5 nanometer, a source resistance of 100 ohm micron, and a record chance conductance above 3 millisiemens per micron, the first time in InGaAs MOSFET, or in any 3-phase field effect transistor. And also achieved a second best subthreshold swing 69 millivolt per decade. And the advance of the device technology also allow us to study some underlying physics in the 3-phase MOSFET. I give you two examples here. They are the impact of the channel thickness scaling to the 3-phase MOSFET characteristic, and the physical origins of the offset leakage current in high-performance InGaAs MOSFET that has bothered the community for a long time. And here is some future works that I will propose as the futures for this project. First of all, I've relatively placed fewer emphasis on the interfacial characterization in my thesis. And I was asked many times for this question in the conference and in emails, so this is a very important question. Given that our intrinsic gate region has subjected to many RIE process, but still maintain a very good electrostatic integrity and the subthreshold characteristics, so this is a very interesting problem to explore. But due to our very special architectures, the quantum well architectures, we will need to carefully decide the layouts and the layout and the device to be tested for this study. We also need to develop some new models. And for this, a new model developed by Jerome before is the first step to explore this problem. And there's a second problem. Recently in the community, there's increasing discussions about the charge controls in the 3-phase channels versus its transport property. So because of the low density of states in the 3-phase, this might dilute the advantage of the high transport property of this material system. So most of those work are theoretical. So I have a feeling that the experimental work on this subject is lagging behind. So to address this problem, a very good starting point is looking at the MIT virtual source model, MVS, developed by Professor Antoniadis. And this is a unified model for the transport and charge based on the concept of effective mass. So I think some beautiful experiment can be derived from this real MVS model's concept and our device technology developed here. And also discuss that we explore in our device some underlying device physics. This allows us to optimize the design of the 3-phase transistor. So actually we have some preliminary ideas as how we can reduce the off-state leakage current and increase the on-state currents in our particular device structures. And lastly, as I discussed before, comparing to HAMD, the MOSFET is free from the gate leakage problem. We can scale the EOT so much thinner and place the N+ source and drain so much closer to the gate. So I think that the potential of the InGaAs MOSFET has not been fully unleashed. And so the performance should be whatever a HAMD can do, I think a MOSFET can do even better. So it allows us to explore the potential applications of a 3-phase MOSFET in the domains that is previously dictated by HAMD, for example, the RF applications. So here I come to my last part of my talk. I would like to acknowledge a list of people. First of all, I would like to thank my advisors, Professor Dimitri Antoniadis and Professor Jesus Del Amo, for their continuous support, advice, encouragement, and everything throughout the course of my thesis. In the beginning 2 years, I was really struggling with a lot of difficulty in process experiment. For example, the experiment cannot repeat by itself. So thanks to their advice, support, and patience, I can overcome all those problems. And in the recent times, when I arrive at a relatively good device, I have the opportunity to discuss a lot of device physics problems with them. I have been benefit a lot from these discussions. And From those discussions, I have the advantage of seeing how difficult it is to really get to know something, and how difficult it is to really, how careful you need to be to check every assumptions and every experimental data. So from them, I see a very unique characteristic. The very fine, I would say, it's a very classic spirit of scientific research that I admire very much. And then I would like to thank my thesis committee, Professor Thomas Palacio, and for his continuous support and advice throughout the course of my thesis. I have benefited a lot from the amazing characterization equipment he has in his lab. I would like to thank other MIT faculties for their advice and teachings to me. And then I would like to thank the PTC, particularly Professor Judy Hoyt and Dr. Vicky Jerome. At the beginning of my thesis, I was challenged to be the first one who introduced a lot of 3-phase material to CMOS tool. And thanks to their support, we decide very carefully the benchmarking experiments to see what is the reasonable path for the 3-phase to enter the CMOS tool. And those efforts, I benefit greatly from them. And I would like to thank the MTL staff and administrative. So as you can see, that we have a really strong competitions around the world for this research. And thanks to their efforts, keeping the equipment working so effectively and keeping everything running so fluently, we have the opportunity to catch up with the state of the art and make this research possible. I would like to also thank the SCBL staff, Mark. And the SCBL is a very splendid tool. It's a wonderful tool. And more wonderfully is maintaining in a very good manner and so accessible to students like me. And my research is greatly benefit from those. I would like to thank the members from Professor Jesus de Alamo and Professor Jianqiang and this group. I mentioned a lot about the technology heritage. So it was the members in our group, the alumni and current students who developed those technology and pass along this technology. So I hope very much that my work here can be part of this heritage and pass along in the future students. And together with our group and the students and postdoc in MTL in the 6th floor and other friends in MIT who we have worked together, study together, play together, and eat together. That make my MIT life so much colorful. I would like to thank our funding agents and collaborating institutes. And lastly, I would like to thank my families for their support throughout the course of my MIT's life. Thank you.